Okay, so now let us study the purely geometric way to reactively avoid agents with each other. I again start off with a pretty bad assumption. So that's the robot that we're trying to avoid, and there are agents which are R1, R2, R3, R4, and let's consider all of them circular in nature. And this time, let me not consider the velocities of the different agents which are moving around. So, one of the problems that, of course, I have is that my robot has a radius rho r, and therefore let us make this as a point and inflate all the others appropriately. So that's R1, and I'll not write it up. Let's say it's all the ones with the inflated radius. So that's R2. Let's say that's R3. And this one is, what is a R4? So these are different agents which are around, and let's have R5. By the way, these can collide with each other after inflation by the radius of the robot r. So there's no reason why the inflated ones cannot collide with each other. Now what we do is that we of course have a goal that we need to avoid. Now when it comes to velocity obstacle method, of course, what really happened about that they were trying to maximize their speed, and that led them very close to each other, and which is problematic if they should really be avoiding each other. Of course, I can specify it as a constraint that the angle of the velocity vector will only be considered such that threshold clearance over here is left when they are very close to each other. That's possible. However, here what I'm going to do is I'm going to have exactly the opposite way of working. So I'm trying to say that let us maximize clearance, let the robot go with largest clearance from each other, which is how many of us walk. So when we walk, we don't kiss each other. We try to go as far away as possible, unless we are friends, unless we are walking together. So it's as far away as possible. It's sufficiently far away. So let's find out the angular range in which I can move and the angular range in which I absolutely cannot move. So with every agent, I am drawing lines such that so this angular range I cannot cover, I'll enter into a collision. This angular range I cannot cover, I'll enter into collision. This angular range I cannot cover, I'll enter into collision. Then this angular range I cannot cover, I'll enter into a collision. That's again an angular range I cannot cover, I'll enter into collision. So I'm modeling which all angular ranges are not possible. And there may have been many obstacles far away, so I say that my limit of angular range is limited to a Dmax. After Dmax, I don't care about. So if there are agents which are around over here, I will absolutely not consider them up. Now this leads me to what is called as the gaps. So that's my first gap angle, that's my second gap angle, and these are the angles which I can use in order to navigate. There are also kinematic constraints, so let us take that. So I say that the agent cannot move outside this range because of a kinematic constraint. I'm assuming the agent is currently looking at here, so it cannot move around this angle as well. And there are visibility constraints. So if you have a stereo camera which are looking at all these circular obstacles, the stereo camera will have a circular visibility range of, let's say, 50° minus to 50° plus. They cannot see beyond it, so you don't know what happens after it. Similarly, if you've got a series of ultrasonic sensors, they may only be fitted at, say, minus 90 to plus 90. You cannot see after that. I'm traveling at a certain velocity v. Depending upon the velocity, there's only a specific curve that I can take. I cannot turn more than that radius. That means my immediate velocity has to be between some kinematic constraints to some other kinematic constraints. So that's the visibility constraints and that's the kinematic constraint. So this is the effective range from which I can choose the angle, which will be feasible, which will be realizable. And basically that means I can see another gap over here, which is gap 3. Now, I need to select one gap, and this time let me say that I select a gap that has the maximum angular coverage. So that's the angular coverage of the first gap, that's the angular coverage of the second gap, and that's the angular coverage of the third gap. So third is extremely small. Second is, okay, that's a tough one. I think second is larger than first. So what I see over here is theta gap 3 is less than the angular range of gap 2, which is less than the angular range of gap 1. And I haven't really covered it up, but how I find out the different gaps is, so let's consider just one with a radius of rho r, the radius of the robot, but rho o. So that's the tangent, that's the angle that I need to find out. So that's the obstacle O. So let's say this is the angle gamma O. So that's 90 degrees. So I have sine gamma O is equal to rho r plus rho O divided by the distance between Q. That's where my robot is, to O. So that's how I get this angle, and then I have, this is my coordinate system, which is xy. So this angle is theta O. So I say theta O is equal to a tan 2 OY minus QY OX minus QX. So the angular coverage of this is, let's say, theta OL to theta OR. So the angular range of this is theta OL to theta OR, both inclusive, which is theta O minus gamma 0 to theta O plus gamma 0. And because it's in the range of minus pi to pi, the cyclicity will have to be dealt with. And similar to velocity obstacle, where I plotted them on a straight line, so I'll plot them on a straight line from, say, minus pi to pi. And I'll just say that, okay, this one is not possible because of this. this one is not possible because of the second obstacle, this one is not possible because of the third, and so on and so forth, then these are the kinematic and visibility constraints minimum, these are the kinematic and visibility range maximum. So same calculation, and then I'll get in all my gaps over here. So that's the exact thing that we have done over here, which is to satisfy gap. So now what I do is that I select a gap which is the largest. So gap 1 was the largest, so I select gap 1 as the gap that I need to move. So this problem can now be stated as, I've got my agent over here, and there is a gap, which is gap 1, which is bounded by this. So for some O1 it will be the R, and for some O2 it will be the left. So I need to maximize it up. That means I travel straight at the bisector of it so that this angular range is maximized. So I say theta desired is equal to theta O1R plus theta O2L divided by 2. Or if you understand it better by number line, so that's my line. This is the largest gap as it appears, it's circular. So this is my theta desired. Now the calculations are good. The only thing that I did not care about is what is the goal. So in none of these calculations I did a goal. Now my philosophy so far was always don't let the agent deviate more than alpha. So I always said this is the angle to goal. So from the angle to go, I go minus alpha to plus alpha, and I always restricted my agent to move within that period. So the agent could never have a deviation more than alpha. That was a constraint that I kept, that my agent can never go at a deviation beyond alpha. Here I did not put that constraint to add a more flavor to it. So how do I get goal-seeking behavior? So I say that this is the obstacle avoidance behavior. And similarly, I have goal-seeking behavior where I just go to the angle to goal. Where the angle to goal is, of course, a tan 2 gy minus qy gx minus qx. So now you've got two behaviors. You've got the obstacle avoidance behavior and you've got the goal seeking behavior. And therefore let us do one thing. Let us take the weighted addition of both of them. So WOA times this behavior plus W goal times. Where W goal plus WOA is equal to 1. Weighted addition. And that's exactly what I started off with. I said sometimes what we'll do is we'll have obstacle avoidance behavior, we'll have goal seeking behavior. I'll invoke both the behaviors. I'll get some desired navigation from both of them. I'll just do a weighted addition of both of them, and the fusion is what will give me the final output. So that's my theta desired. So that's the same fusion that I talked about. And I also said that this fusion will depend upon what the context is. So I need to add a context over here. And the context is again the same, near obstacles. I am more obstacle conscious, and away from obstacles, I am more towards go straight to the goal. So that's a fusion, and again, fusion you need to take care of. Sometimes two opposing behaviors, avoid this obstacle from the left, avoid this obstacle from the right, and you bang to the obstacle, weighted addition. That's why as we go nearer to the obstacle, the goal will be gone, and first avoid the obstacle, we'll care about the goal later. So that's the one that gives me theta desired. Theta desired is exactly where I want to go, so I'll control my angular speed as my current angle deviation. So I want to get to this orientation. This is my current orientation. This is my error. So P controller, this is the error that I need to minimize. So my angular speed will be the constant times this error, so that this error gets minimized. If I'm traveling at exactly this angle, then this error becomes 0 and my angular speed is 0, which means keep going straight. My linear speed is, of course, again a constant times the distance from obstacle in front. So over here, after enlargement, I basically look at after how much distance do I have an obstacle. And if it's far off, then I enjoy a high speed. If it's close by, I enjoy a low speed. And that's how I adapt it up. So again, this Dmax will have to be adapted. Sometimes Dmax is so large that you have all obstacles around, and you have to reduce that up so that you at least get one gap. Otherwise, if there are no gaps, then how will you move? There are no gaps, so you have to reduce Dmax so that you move. So the distance from the obstacle in front, it tells me at what speed can I move in. And there's another spatial modeling. So here I'm trying to find out gaps in terms of the angular coverage. That was my gap 1, that was my gap 2, and that was my gap 3. Sometimes what you do is you say this is your spatial gap from this tangent to this tangent. So where this tangent touches this obstacle to this tangent touches this obstacle, that's your gap, and that's your length of the gap 1. Similarly, where this tangent touches this one over here, and where this tangent touches this one over here, this is your length of gap 2. Here, of course, you need to find the shortest distance between this and the line, so this is length of gap 3. It can be calculated from geometry, so you know the equation of the circle, you know this thing, you know this angle. I just calculated those angles, so you know the equation of this line, you know exactly where this point hits, where this line hits this point. You can geometrically find that out. Similarly here, more importantly, theta gap 2 was known, this distance was known, this distance was known. So we knew it from the previous formulas. We knew this distance, we knew this distance, and therefore you can actually find out from the law of cosines what is this length gap 2. So plotting it around over here, so any one of the gaps, so that's your, let's say, R3, that's your Q. So I only calculated this gamma 0 based on the fact that this is dq comma r3 position. This is rho r plus rho of robot 3. This is a 90 degree. The tangents cut at 90 degree. So you know this length. And if I plot this triangle more clearly, so you know this length from this formula, you know this length from a similar formula, you know theta gap from a same formula, angle subtraction, so law of cosines gives you the length. Now geometrically you find out the middle point of this, and then you move exactly to the spatial middle point of this, which also solves the problem. Except for the mathematics is using law of cosines, which is a little bit more involved. But then the essence is that using geometry alone, I can calculate where I should be moving in order to maximize my either radial clearance or my spatial clearance and move in a respectable distance from each and every person around. The only problem is it's only obstacle avoidance and it is not goal seeking. So goal seeking, I'll add a different behavior. So I say a fusion as W1 times obstacle avoidance plus W2 times goal seeking, and I add the obstacle avoidance, the goal seeking behavior similarly.